less than equal to would include the boundary, that would be a closed neighborhood. Alright, so we have all the nuts and bolts in place. Let's write down our first order condition. So I'll write it down and then we will interpret it. It's very straightforward. It is the generalization of what you had expected from calculus of single variable. What was in calculus of a single variable, what was your identifier of a minima? F dash equal to 0. What do you expect is going to happen in the multivariate case? Grad f star is going to be equal to 0, right? That's it. There's no surprises there, but let's write it down formally. Okay, so if x star is a local minimizer, but I also have to say that f has to be differentiable, right? Is okay, but where in a open neighborhood of x star, right, then grad f of x star is equal to 0, right? So this is the if and this is the then. Okay, so let me take a very quick example. Supposing I wrote my function f was a function that captured a chess game. Okay, and to win chess I have to minimize f. Can I use this theorem to identify a possible solution to a chess game? F is not continuously differentiable because first of all the variables themselves are discrete. I cannot make a continuous move, right? I can make a discrete move in 1 step, 2 step, or whatever the way the horse moves. So be careful of where you apply this. That's why this requirement that f is continuously differentiable is not a formality. You need to make sure that your function is differentiable. Now chess, you may say, oh, okay, we're never actually going to write an optimization problem for chess, but it may happen that in your engineering problem you're designing some antenna surface and you've discretized it into discrete variables and you try to apply this, it will not work. Okay. Right, so this is your first order condition. It is also a necessary condition. Okay. Further, if this holds true, then there is a special word, another special word reserved for x star. It is called a stationary point. The only reason I'm mentioning this is because some books will call it a stationary point, so you should just know that there are various words by which people refer to it. Right, so this is quite straightforward. We'll prove this. Proof is quite simple and gives us insight. It will give us actually insight into our first algorithm. So we'll go into the proof. Before we go into the proof, I want to write down the second order condition. Okay, any questions about this? Yeah. Yeah. It is not specified. Okay. So within whatever radius you specify, which is non-zero, that function should be continuously differentiable, right? And within that radius, if you find f of x, grad f of x star equal to 0, you're fine, right? Now it may happen that within this neighborhood you don't find any point where grad f of x star is 0. Then you would have to expand your neighborhood and check, is the function continuously differentiable. As long as the function is continuously differentiable, you have a whole set of techniques available for you to move from a starting point to a finishing point, right? So the thing that enables all this magic in some sense is differentiability. If you don't have it, you're stuck. Then you have to go to other things like evolutionary algorithms or whatever, right? For this entire course, we're going to assume at least first order differentiability. Okay. When you talk about convex functions, etc., they're already differentiable. So it covers a vast range of engineering topics already. So it's not restrictive by any means. Okay. Linear programming, if you've heard of linear programming, for example, again, differentiability, etc., is there. So it covers a large range of optimization. Okay, so now let's note down our second order. These are conditions for what? For checking whether the point I have got is a local minima or not, right? And why do we need a second order condition? Can someone point out looking at this page? Because I have only got a necessary condition, I have not got a sufficient condition. So the second order condition is actually what is going to give me a sufficient condition. Since it involves second order, it may be a little bit more difficult to evaluate. Okay. Now for the second order conditions, we are going to second order derivatives. So my requirements are a little bit more stringent on the function. So what do I require? Let's note that down. Obviously, the Hessian should exist. Not only should it exist, it should be continuous. Exists and is continuous, and again we'll use the formal phrasing on an open neighborhood. All right. So we will start with the necessary part. Right. So it states that if X star is a minimizer, right, then what all happens? First is what we expected from the first order condition. Grad of f of X star should be 0, right? No surprises here. The second condition, in I think a few previous classes, we had a brief discussion about it, since it involved second order derivatives, which was that someone wants to take a guess, what might be this second condition? If I were doing this in single variable scalar calculus, what would be the condition for, I mean, what else would I need to have? F double dash is greater than 0. Now I have to generalize that to Hessian is positive definite, right? Exactly. So this gives me the necessary conditions, quite straightforward. Now let's come to the sufficient conditions. Sufficient will work the reverse way, right? Here I had a if and a then. Now I'll start with the then and come to the if part, right? So if both this and the Hessian at X star is positive definite, okay, then X star is a local minimizer. This is flipping it the other way. There is one small correction that we need to make here. Can anyone point it out? The hint is weak strong. Right? If I want to, if I want my minimizers to include weak minimizers, then I'll have to relax things a little bit and do what? Make this positive semi-definite, right? And then this will be positive semi-definite, right? So let's just mention that weak, if I'm talking about weak, then it has to be positive semi-definite. If I'm talking about strong, it should be positive definite. Any intuition as to why it should be positive definite? The intuition, if you want a geometric intuition, it's again similar to the one dimensional case. It's that if you look at okay, so when I write a second order approximation, second order Taylor's approximation, what is the, in one dimension, what am I approximating my function as? A parabola, right? A parabolic equation, because I'm stopping at x square. So something a plus bx plus cx square in general is a parabola, right? Now, if I want my point to be a local minimizer, what can it be? Any kind of parabola? No, it should be a parabola that is upward opening. Then that lower, the bottom of that parabola is the minimizer. Now, when I come to multiple dimension, that same intuition now, instead of a line, think of a bowl in n dimensions, right? It's hard to visualize beyond 3 dimensions, but imagine a bowl in 3 dimensions, I mean in n dimensions, and what you're saying, and that whether or not it's a bowl, as opposed to a downward bowl, a saddle hump, it can take various shapes, so it can take some really arbitrary shape. But if I want that point to be a minimizer, that means there is no point of the function below that point. It has to be a bowl, and that geometric property is captured by the Hessian being positive definite. So it's a one-to-one geometric translation. Okay, so if you want, we can draw this. So the geometric intuition. Because if you remember, second derivative of a function talks about curvature, right? If the curvature is always positive, then it's always one kind of a shape. Correct. It's always in, yeah. Don't think, I mean, it is a matrix, all right, but keep the geometric, I mean, what is a matrix? It's just a collection of, in this case, 3 values, 3 mixed derivatives, right? So there is, for example, if I have x1, x2, it's going to be this. This is essentially what is there inside the Hessian, right? And all of these second order derivatives are talking about the curvature of the function in these dimensions. That's pretty much. Yeah. Correct. Correct. And the intuition which you're mentioning will get actually, we'll open it up properly in the next few slides. Okay, good. Yeah, it's always good to have this geometry in mind. So having stated, does anyone have any other questions on the statement of the second order condition? Yeah. At that, in the neighborhood of that point. Well, if you are talking about whether it's continuous at just one point and not at any other points, is that what you're saying? No, if it is, see, if you are saying that the derivative, I mean the Hessian exists, and if it exists, you're saying therefore it's continuous, right? Well, I can have a second order derivative which exists but need not be continuous. I can cook up functions like that, right? Can you think of an example? For example, a function, let's come down one derivative. Let's talk about first order derivative. This function is continuous. Is it differentiable? So continuity does not imply differentiability, right? So there's going to be one point where the derivative is not defined. Well, the derivative here exists at all of these points, but not at this point. But what this theorem is saying is that in a small neighborhood of this point, you check whether it's continuous. That's what I need to check. So what is the motivation to have a neighborhood around that point is that this will come to the next what we're going to talk about is come up with some algorithm. We don't see, this is just a check or a test for a minima. That doesn't really help me, because when I start my problem, I don't have any candidate. I have a starting point. There's not much fun in checking the starting point. Most likely I would have started at the wrong point. I need some way to move. And if I want to move, I need this open neighborhood in which I can move. If that open neighborhood does not exist, then what use is it? It's a nice theorem, but it doesn't help me. So that's why the open neighborhood allows me to move to a better point, That's the motivation.